having only a 4-bit 1 over x, or to have a 4-bit by 4-bit adder or multiplier. Good. So let's see. Let's do the introduction and then we start, and then you will see what's the task are. So the motivation to look into that one is because if you look at the AI trend at the moment, there are the NPU calculations and they use floating point numbers. And if you use floating point numbers, the bigger they are, the more computing power they need. And so the motivation is to have floating points with a very small number of bits. So I looked into that one and looked at some what kind of floating point numbers are there. So normally you start with signed integer with a sign or a complement bit, and then you have the floating point. So normally you have a signed parenthesis and an exponent, and then you get a 8-bit FP8, which is then called exponent 3 parenthesis 4. So you get a 1-bit sign, 4-bit significant, 3-bit exponent. So this would be a 8-bit floating point number. There are also some smaller numbers, and down here, this would be the 8-bit where you have one sign bit. Then you have 4 bits for the exponent, and then 3 bits for the parenthesis. And depending where you look at, you can map then this one to different formats. And there are some formats which are applied by the manufacturers, like NVIDIA or like AMD, and then there are some formats which are IEEE standardized, so you get a standardized format there. So I thought about that one. Okay, what can we do? There can be a 3-bit mini float, there can be a 4-bit mini float, and so I am stopping at a 4-bit mapping, because this is what we can easily create with our tools here in this lecture. So down here you have a typical mapping of the 3-bit or the 4-bit. If you have the three bits, you see the lower bits and the upper bit. The upper bit is just the sign bit, 0 or 1, so you have only a 1, a 0, a 1, a minus 0 and a minus 1, and then you need some infinity, because if you divide by 0, then there should be something sensible happening and not a blue screen. So we have the infinity and the minus infinity, and then it can be that during your converting some input into a number, it can be that it's not a number, so you have also an NaN, so that you don't have a number here, and you show that. 4 bits would be the similar here, plus, one line for plus, one line for minus. You see, okay, the number of numbers are increasing. There is still the infinity, plus infinity, minus infinity, and the NaN, and there are the plus 0 and the minus 0. And you see there are some NVIDIA formats here, 1 to 1. So you actually see that there are numbers which have only 4 bits. And they are used for the calculations of your AI operations. So what happens with us? Yes, if you do the mapping, then the question is how big will be your truth table to do your operation. And so far we only talked about building truth tables with some multiplexers and some lookup tables. So this is the kind of tool we have. And so now the question is, what do we have to map on this one? So the one is, you have to map a decimal number to a binary number somehow. This was the table I showed before. You just have the codes from 0 to whatever, 7 or 15 or whatever, and you map that to plus, minus, infinity, and some ratios. Then you have the truth table size here is because you have n 2 to the power of n combinations for the input, so you have also 2 to the power of n combinations for the output. Then you can have the minus operation and then the 1 over x operation, and since you are dealing with a floating point, you are doing not 1 over x, but you do the maximum number divided by x, because otherwise you get not a good outcome. So, and if you do this one again, you go in with 2 to the power of n, you generate a 2 to the power of n, so this is the truth table we are getting. And to be limited with our truth tables and the number of transistors, so we are starting today with this one, a truth table size 2 to the power of n, where n is our 4 bits. So we have a 16-bit truth table, and my goal today is to get all the steps for getting from a truth table to a chip with pads, to a layout of a chip with pads, and have the simulation there too. So we will see whether it will fit in the 90 minutes or not. And then of course there is the add, multiply, and the power, where you would have put in 2 times 4 bits number, so we have 8 bits in, and this is a 2 to the power of 2 times n, and that would give you then a much larger truth table, not the 16 length of 16, but the length for 4 bit then of 256. And I implemented some option to generate this one, so the goal will be for the last laboratory, yes, we will do one of the truth table sizes here in the today. And then you get the task, I put all the ones who passed the laboratory one into some table, so that you will get basically one line of these truth table here with 16 bits, so that you can do your own. This would be the first part, and then to basically have an open end, then you could also try to do truth table size 2 to the power of 2n, and we will see how that works today. And so this would be then the open task, and I hope that I have a slide before starting. No, this is some information about Intel floating point unit, a very old one with 8 bits. Then the truth table implementation for a full adder. Yeah, so let's shortly look at that one. So what we are building will be, if you have a truth table, yeah, then you see on the left side you have A and B and a carry in, so this would be a full adder, and you get a sum and a C out, so you get 2 bits out. And then if you have 3 inputs, then you have 8 combinations here, you have here 8 outputs here for each of the S and the C out, as we talked in the lecture. We say, okay, I just go down here and take their hex number, so the first hex number would be 0, 1, 1, 0, so this would be 2, 2, 4, so this would be a 6, this would be then a 1 plus 8, a 9, so there would be a 6, 9, and you would basically multiplex these 2 and 6 and 9 with the A, so that you get basically your first output. And you can write it down here that your S would be a LUT with 3 inputs, and it has a 6 and a 9, and you do it by having a multiplexer 2, 6 and 2, 9 with the upper bit here. And then you can see, okay, if you want to do the LUT 2, 6 with a minimum number of transistors, you can form it like this one. And if we have that one, then we can easily, our VLSI design system can easily synthesize this one into a transistor circuit. So our goal is to have a truth table, to map it to multiplexers and lookup tables. And then if we have the multiplexers and lookup tables in VHDL, we can put it into the VLSI system and then generate our circuit. If we have our circuit, then we can simulate that one. So we need some stimulus for the simulation. We have a tool. We will have a tool there, and then we can get our output. Good. And we see as we go up with our number of inputs, our total transistor number will increase a lot. And our goal will be to get the total number of transistors as small as possible. So this is our objective. And so we will start with a guided generation of our circuit. So our goal for today will be, yes, we have a 4-bit truth table for a division, where we have the original code 0, 0.25, till minus infinity, plus infinity. So this is a mapping of our floating point numbers. And now I want to do for all these input codes from binary 0 to 15, we want to map it to something sensible, where we have the maximum. So it's a 3 divided by our x. So if you divide 1 over 0, the positive, then we will get plus infinity. 0.25, 1 over 0.25, we get to the 3. 1 over 0.5, we get to the 2. 1 over the 0.75, yes, this is nearly 1. So it's more than 1, but since we don't have any any number here which is more than 1, we have to map it on 1. 1 over 1 is also 1, 2. 1 over 2 will be the 0.5. 1 over 3 should be 0.33. We don't have a 0.33 in our range here, so it will be 0.25. The next one, plus infinity, 1 over plus infinity will give us our 0. NaN will remain NaN minus 0.25, so we basically have the same here in negative. And yeah, and the minus infinity, since we don't have a minus 0 but just a 0, it will be 0. So our task is to transfer this truth table into a circuit. Okay? Good. So let's look at this one. So first thing is so we want to have this false truth table. Fortunately, I have here implemented that you can get for this one the table into a CSV. So you will only get, interesting, see there's one missing, the minus infinity. So you can get this one over here. And now we want to generate for this truth table a VHDL, and unfortunately I have down here a tool where you basically, we put there for our truth table, we have here a module named test which will generate our VHDL code. We have here our codes where we have our input, the range of our numbers. We have down here our output. We have here an option that we have only one input code so that we can get our translation table. There will be another option where we have two input codes so that we can generate a complete table for an add or multiply operation with 8 bits. And then if we put both of these ones in, so you have the choice which kind of codes you have. You have the choice which kind of codes your output. Both code ranges should be the same, otherwise it's not working. Then there are some lookup of some numbers which are not there. And then you can hit down here to generate the truth table. So you see here down here, yes, This is my input code. At the beginning you just see that you have 16 mappings, then you see, yes, your original code, then for each code you have the binary combinations, then you have the code out, so the mapping we had before from our list, with the associated code, which is plus infinity, is the code 7, as you see down here, and so we have to generate a 7. So now, this is here our binary output we are expecting for this translation table. Then we can go in there and say, okay, for one column here, the output 3, I have to combine this with our lookup tables and our multiplexer, so I get here these hex numbers. So I start here with 0, the 4 zeros. Again, the second one is also 0, then I have 1, 1, 1, 1, so it's an F, and then I have a 1, 1, 1, 0. F7. So I see, okay, for this truth table, I have my equations of the output codes, which is 0, 0, F7 for out 3, F1, E1 for output 2, 3, 2, 2 for output 1, and for output 0, 5, 4, 4, 4, according to my truth table. If I change my code mapping, then these hex codes will change, and then my structural VHDL was changed. So now, to make life for you easy is to map this one into a structural VHDL for our VLSI design system. And this is what automatically is generated down here. So I have my entity test as I specified at the top. I have my 4 inputs here because I had only 16. I have 4 outputs because I have only 1 input. So these are my entity where I say, okay, these are my inputs and outputs. And then I do my architecture. I need, because I didn't program to use only the lookup tables of the hex numbers I need. There will be all the hex lookup tables present, even if I don't use them. And then I have one multiplexer with 2 inputs here. And then I have my signals. These are all the components I will be using. Then I have my signals. First signals for the LUT2, and then the signals for the WUX2. So for the output 0, output 1, output 2, and output 3. So I need some signals, so I have them here. Good. And then you see, okay, first I have the instances of all the lookup tables, where probably I don't need all of them, but I implement them anyway. And then the outputs I label conveniently with net underscore 0 to net underscore f, depending whether I have here a 0 or a f. And then I realize my outputs. So if I have my output 3, 0, 0, F7, oh, unfortunately, see, there is still a programming error because this will be mapped to output 0 and not output 3. So I have to fix this one. So you see it's an ongoing project, unfortunately. Anyway, but you get this out here, 0, 0. So I get here 0, 0, F7. I get the outputs here of the first multiplexer staged, and then I combine these to my real output. And everything will be selected by my input 3. Because the input 1 and input 2 are used here, the input 2 are doing then the second multiplexer stage, and the input 3 is doing the last input stage. And then I have the same for the output 2, for the output 1, and for the output 0. And unfortunately, I have to fix this one. Okay. Good. So now we have the VHDL, so we can start our electric and see how can we transfer this VHDL into electric and do something. And we have down here our step-by-step instruction. So we will open our VLSI design system, and I hope you do that together with me. Good. So you have your VLSI system. And you need here two libraries, sclib and pads form. So you go back to the web page. You see here is the sclib library, which you download into your local directory. And there is a pads for you under library, so you create a directory, put these two in. And later we need also the pads multiplier 2x2 array, which we also put into the subdirectory. And probably I have to do that I and you see here I have already done the lab 5, so I will, because I tried it once, so this is lab 05A. So I tried it out once, so I expect that I will get some more problems today. Not only the numbering of the outputs, but something else too. So I have my sclibs, I have my pads for you. I have my pads multiplier. Good. So I have these, so I should close these, and then I have to, because they are in a different directory, I have to close these. So as soon as you have downloaded this, then you open the library. As you see, I'm in the wrong directory, so I'm in the. So you go into your directory, you open the sclib file, open library. We open our pads. Good. So now we have the libraries we will use. And now we can get a new library where we put all of our laboratory 5 in there. So my name for the library should be lab05jlib, so for me it will be lab05A. You can, okay. So now I have my library where I can work, and now I want to create basically our project where we try to generate our new VHDL cell name. So we have basically, so we will go here, we will go cell, new cell, we will select here that we have a VHDL code. We will say here, what's my naming rules? diff at multiply. So what we are doing is a division, so we will have a diff underscore and then the line number. We have only one line number in our multiplier, or so we can, if we just implement one line, we will put a 0 to f there, and then you could put your initials there. So I will put in a diff. So we have here a diff underscore 0 JV for my name. Good. So now we have in this library, if I click on this, if I can click on this, I should see this, and this is still empty. So now I can insert here my VHDL code. And this will be very interesting when that works or not. So I scroll up here. I hope you generated this code already. Good. Anybody not having this code?
Could you show how to generate again, please?
Good. So up here, our module name we should probably change. So my module name was diff underscore JV. This was my cell name. Oh, and then my output. This is very bad because I can't type there. I just can copy in there. So I have to get this script. So I just paste it in here. Then I have here inserted my code and here my output code, my desired output code. So both of these are basically the lines I have. This is a line I copy in there, which I got from this table. And this is basically the second line here. The first line I already is per default the correct one, and the second one should also be per default the correct one, hopefully. As you put both of these in, the codes and the output, as you have here the operation one input code, if you generate the truth table, you should get this truth table plus this structure lookup MUX VHDL. Yes? This is
Thank you.
okay. So now we want to get all these VHDL code and put it into our VLSI design system. So it ends here with before our Verilog starts. Control C. We go over here to our and do a Control V. And hopefully we get exactly the text in this one. And yes, we need these LUT2Fs to get them. We need the sclib. To get the MUX2, we need the sclib. Otherwise, it's not working. This is why we downloaded the sclib. This is where you look in here and you see, or you should see down here all the LUT. And you should see down here somewhere the MUX. So you see down here the MUX2. So we have a structural VHDL, so it should be easy to do our silicon compiler and convert everything into a layout. Oh, yes, and you see I got an exception, and I see.
So for that we have to change the output of MUX2. Because before you said that this is wrong.
This would be a good thing, yes. We can change here the output 03 to 03, 02, 01, 0. The good thing here is since we will only push some buttons and it will be totally automatically, so if we change it here, it's we can easily redo it correctly. Great. So, okay. 3, 2, 1, 0. Great. I don't know why. And at the moment, great, I don't know why it's complaining about I7, I6, I5 and I4, because I don't see that I have any. Wait, is it the same error with you? So probably, oh, this is an old message. So let's do it again. Tools. Okay. So let's see whether we can do something. Okay, so it wants to have the entity at the very beginning, and I don't know why. One moment, yes. Good. So I get here an error message where I have a cyclic conflict. So this is probably due to my bad settings in my preferences. I have here the number of rows in the cell, which is too high at 10. I have to redo it at 4. Is also not working. So that's and then we have here horizontal, and then I am here on the wrong format, so I have to go first select the layout so that we can go. No, this is good. Good. So let's see again. Preferences. So now I have the metal 1, vertical routing metal 2, number of rows in the cell is 1. Okay. So let's try it with this part again, to look whether we can get this silicon compiler. Okay. Good. So, questions? Did you also get a layout? Yeah.
Are we doing adding or division?
Excuse me?
Or you said you should write div underscore node.
Yes.
Adding.
Basically, for the name here, I thought, okay, I want to know so depending whether you have a divider, adder, multiplier, you can basically start with a diff, and we are starting with a diff. Our line number, because our adder and multiplier will have 16 lines, so you put in there the 0 to F, depending on the line you are assigned to, and then you have your initials, which from here is first name, last name, JV, to get this one. Good. Okay. There will always be popping up a new window here, which you can close. Now I have here a group where I have my layout in here. Okay? Yes?
Could you please show which preferences you use for the metal lines?
For the metal lines.
Yeah. In the schematic or in the okay.
So normally you get these preferences if you select in a layout metal 1 without having this open and then open this again, then it should be like this one. So you have here it should be 1. So you should try out different number of rows. So to get a square layout, you see that you can get an exception because there is cyclic conflicts there. You have here the metal 1, 4, metal 2, 4, and then spacing of the cells to get it as close together as possible. You have the -32, the 8, and the -9 here. And then you get a very dense layout. If you have there some other numbers here, some positive, all the cells will be placed further apart, so you will not get the minimum size of the layout. Good.
You can only
Yeah?
choose solid dotted.
Yes, this you can only choose if you have only the solid, then you are not in the layout mode, but you are in the schematic mode. To get into the layout mode, you go somewhere here into a layout, select something like this, then you are in the layout mode. You see that you have now here the layout, and if you are in this mode, then you can have the preferences. Then there should be metal 1 probably and metal 1 like with me, and then you change the 1 from metal 1 to metal 2, and then it should work. Now I have to check.
Not here, yes. I to open
Okay, so what's your error message?
the other file. Yes. Next one. Good.
So here it says there is no root to 0 in the standard. Where did you get this from? Yes. And I attach I0, I1, I2, I3, then everything would be fine. Good. So, now I need a splice code. Oh, hopefully I have a splice code down there in my. Where's mine?
Manipulate.
Where's my lookup table?
Correct.
let's cancel test. Okay, let's get from here some spice code, which will we modify in a minute. Go here to miscellaneous, and I want to have some spice code added to it. I put it here. I get to the properties. I would like to have multi-line texts. I will put this in. My text size has to be larger, hopefully.
How did you get to the test properties?
As soon as I make in the spice code, there is a very small X. As long as this X is still selected, I can go to the edit properties.
Okay.
And then I get something here. So I will have my VDD, my temperature, I don't know. Okay, my clock. I will replace all these. I will have here 10 nanoseconds times 16 times. I will simulate here for 160 nanoseconds. So this will be my starting point. That I have a transistor model, CMOS edu underscore models.txt, and I have this one. Good. Now I need some input stimulus. And I want to have some output stimulus. Yeah.
Sorry, where did we take the spice code?
You take it anywhere. I took it from. Where's my test? Scan cell test. From here.
Okay. Okay.
Basically, you don't have libraries in there. The current libraries load. So you should first follow the instruction, load the libraries, and then you create your own library as stated in the. Okay? Good. So we have here our LT spice code. Now we want to generate our input stimulus. For the input stimulus we need, oh, this is great. We can basically take this one here, this is also provided. So this is a special format where the truth table from the top. So you have here your 4 inputs, which have all the combinations, your 16 combinations. You have your outputs, which are the expected output values. And then you have a comment, and if you have this text, then you can just simply select all these lines with Control C. Then you go to your simulation in a new tab. You can insert it over here. Good. Oh, actually, I don't know.
Excuse me, sir. Did
Oh,
you
yeah.
reach the last step?
One moment. Yes. I'm not sure about this one. So the last step over here in your where you have your VHDL code. Here's your VHDL code. Then you get here your Verilog code, and here you get the simulations. And here you have a link to a website. You go. So this is where I open this one, and you read all this text here. So you just take all this text, copy it over here, and since I don't know how to operate this one, So now we have to specify here something. So I want to do a simulation with a 10 nanosecond time step. So my clock will be running at 10 nanoseconds. And then I need my input signals, which will be I0, I3 to I0. Then input registers I don't have. Output signals. Oh, actually probably I'm wrong. I just put in this one in the. Okay, Control C. I just need this as the top line. This is the upper one is only to generate a table. Okay. So as we have everything input here, then we just generate our analysis request. And we see, okay, this is our analysis request. Oh, actually, oh, I get output 0, I have output 1, output 2, output 3. We will get the same names from our simulation, so this is not good, so we have to modify it here. So I will do it to O3x, O12x, O1x, and O1, and generate the output. So, good. Now I basically have here my truth table in my timing simulation. So you see I3, I2, I1, I0, I3, I2, I1, I0. I start here with 0, 1, 2, 3, 4, 5, 6, 7 until 16. And I can get now my expected output 03, 02, 01, 0. You see down here, these are my expected outputs. So if I have now for LT Spice the input signals of this one, then I compare my output from my layout to my real output. And fortunately down here there is the LT Spice code. So we select all of this LT Spice code. And you see, otherwise it would be a pain to get all the LT Spice code, and the LT Spice code ends here. So this is all the LT Spice code I need for my simulation. And I go over here, I select my LT Spice code, I can go over here and I insert everything like this one. And then I put it down here. And now I have my, hopefully I have my complete input stimulus inserted into for my LT Spice.
Sure.
Yeah.
What is in the first lines of the LT Spice code?
In the first lines of the LT Spice code.
Yeah, 2. Like this.
So you see, this is a global BDD. So this parameter I don't need probably.
And the down one is 10.
The temperature I don't need either. There comes the VDD, that I have a global VDD.
Oh, okay.
That I include my CMOS EDU models, so that I have a transistor model, and I want to simulate for 160 nanoseconds. Since my clock cycle is 10 nanoseconds, I have 16 stages, so I need 160 nanoseconds. And then all the things about my input signals and output signals come. Okay?
Yeah.
Good, now we're ready, so we can start our LT Spice, right? Spice stack. So you have here your Spice stack. We get the error message about this options no name no page. We just comment it out. And then we see all the things we are expecting. So we see all the sub-circuits for our LUTs, LUT2A, LUT2B, LUT2C. All these sub-circuits start LUT20, and so on. So these are all my LUTs. There are bigger and smaller LUTs. And then comes my multiplexer, multiplexer 2, my subcircuit. And for each subcircuit I can count my number of transistors here. So I know my Max 2 circuit has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 transistors. And I can do that with all my others. And then I get my top cell, and in my top cell I expect the same as in my VHDL code. So my top level cell, yes, in my VHDL code I had all these LUTs here, A, B, C, D, E, F, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And unfortunately, T-Spice is not using the same notation as before. So it has some internal notes here. Oh, because these are not used here, this is why it's arbitrary named. So we are using only probably these ones. I'm not sure. No, this is not true. These ones are used, but the other ones are not used. And then I see basically my multiplexers. My multiplexers for my O3, for my O2, for my O1, and for my O0. So I always have here 2, 2, 2, 2, my multiplexers.
Okay.
And I see, yes, my I0, I1, I2, I3 are going in. So I hope everything will work as expected. So now we can run it. And you see, I already set it up for my output. So if you once add your traces to it, then you can set it up and, oh, actually, I have to look here. Okay, so at some point of time, I should add my description of all these So at the moment you just have to go over here, you add your trace.